Okay. Uh, we're going to look at an idea called transformation of functions. So we're going to look at the algebra. So f at x is the concept of function notation, which means there's some equation that is equal to this. And we've essentially given it a name. We're calling it f, and whatever's in the bracket is the variable that is in that equation. You can technically have something like this. It could have multiple variables, x and y and z, and all those variables could be in the function. For high school, we focus on one. It's a little easier that way. Actually, I'll leave it there. Why not? What we're going to be doing is transforming functions. So I'm going to write the general equation of a transformation. So we'll call that general. Oh, that's not very good spelling. General equation. General equation is usually written like this. You have a, and then there is some function, okay, with a set of brackets. Let's see what letter they use for you guys. Usually it's a B or a K. Okay, K they use instead. Could be sometimes used as a B. It doesn't matter. It's the position that's important. X, subtract. You guys use the letter D. Oh, thank you. Turn that off. And C, is that what's on the outside? Yeah.
Yeah, plus C.
What color haven't I used yet? Yellow. Can we see it? Yeah, we can see it. Okay, good. Okay, so this is the general equation, and we'll talk about essentially what these do. A and K do stretches and compressions. Okay, so we'll call it S and C. Stretch and compression, and technically flips too. We'll put an F. S, C, F for all of them. The difference is A does vertical stretches, compressions, and flips, and K does horizontal stretches, compressions, and flips. And you'll notice that the vertical stretch looks like a horizontal compression, and a horizontal stretch looks like a vertical compression. They're a little different. And then you have D and C. These are transformations. So this is actually a horizontal transformation. Let's use T for it. And C has to do with vertical transformations, depending if they're positive or negative, okay? Once we know, or once we're able to recognize like variables as a part of a function, we can take any function, that's what f at x stands for, and we can apply these numbers and we can regraph it any way we want, okay? So we're currently looking at the algebra of it, but the goal of this is to very quickly graph something as long as we know a parent function. A parent function just tells us what type of function we're working with. So for instance, a quadratic, I'm gonna call it q at x, okay? All that is I'm naming a function q. So all these letters in the front, they're just the names. They use one symbol instead of giving it a really long name because it's annoying to write, but any symbol can be called it. So we assigned q to, or q at x is equal to this. And this is the parent function of a quadratic, okay? So what I'm gonna quickly do is I'm gonna jump over, here we go. We'll call it q at x is equal to x squared. And that's what our regular parent function looks like. It's a regular quadratic. We can use other ones. Let's say a root. R at x is the root function, which is the square root of x. We'll show that one too. So we'll say R at x is equal to square root, whoops, that's not z, x. There we go. And you'll notice this one technically only draws the positive values. It's because it has to pass function notation. I've written it as a function. In order to be a function, it has to pass something called a vertical line test. It has to go up and down. So if you were to draw this bottom part down here, it would no longer pass the vertical line test. So as a relation, we can do it, but if we're drawing the function in technicality, we draw like one or the other there. Any other ones you guys do? Reciprocal functions, are you doing? Are you guys using that? Okay, we'll just focus on the big pieces right now. So we'll use these two functions to start with. So what we're going to discover is that depending on what letters we use, okay, with our functions, they're going to transform around the page. So with this being the basis, let's jump back to this. I'm going to hide this one for now. And I'm going to redraw. Q at x is equal to that. So I'm going to say f at x is equal to, and I'm going to start with typing in the word q at x. So this looks odd, and I'm going to say plus 3. What we just did there, okay, can I write up there? Oh yeah, I do it this way. What we've done here is we've taken the original function q at x, that's the one that's read here, and we've essentially added 3. We've vertically moved it up 3 units. So 1, 2, 3. And every single point has moved up 3 units. And that's the idea when we jump back. That's the idea of C. We've essentially added 3 in our case to C. And that's what a vertical transformation looks like. And if we were to do the opposite, or not the opposite, but something different, I mean, I guess you can call it the opposite. Put it to -3, you'll notice that it jumps back down. If we go to -3, it goes down there. Now this made something look different. You see how it looks thinner? I'm going to explain that in a minute. But essentially all I did was move it down 3 units, okay? So what we've just seen there is the value of C. So what I'm going to do is I'm going to make a note here so that we have our general equation here. We'll say g at x. We'll call it g at x. The reason I'm calling everything a different name is really you should be doing that. In function notation, the reason you use it is you give different names so it's easy to refer to. So if I say q at x or r at x or f at x, you know that I'm referring to a different equation every time. So if we always say, which we're used to using, this replace the value of y. If we always say y, if I say y equals, you're kind of struggling on a page when there's many equations. So this is essentially the concept of naming your equations. So g at x is equal to, we have a, they use a big, I don't know, I can't make a fancy f on this one here, but that stands for the function k x minus d and bracket plus c. So what we've just done here with the -3 is we've essentially put a c value on that function. Okay, yeah. We'll turn that off. Same idea, let's manipulate it a little differently. This time I'm going to go in here and I'm going to say -3. I didn't turn it on. And if you notice, this is now moved from the original 1, 2, 3 units, but in a positive direction. So just be aware that -3 moves it in a positive direction, and that's because there's already a negative in the equation. Okay, and because that negative is there, we're really actually putting in +3. We're getting used to what's really happening is you're going x minus +3, so there's a +3 movement. But because that negative is already there, wow, I write really good with the mouse. We simplify these operators, so it becomes x minus 3. Okay. Okay. And then we'll show you the exact same idea here. I didn't know I could write so well. If I were to say positive, hey, it's shifted to the left. Well, what's happened in this case, okay, is we have a bracket and we have x subtract -3. So we have 2 negatives beside each other. 2 negatives simplify to x plus 3. Okay, so that's what's happened in that case. So what we've just done there is we've now dealt with our letter D. These were our horizontal movements, okay? Usually those are the 2 easiest. Inside of the brackets, outside of the brackets, moving up and down, left and right. We're moving the exact same thing. Where it gets a little trickier is the next piece. The next piece has to do with vertical stretches and compressions, okay? So I'm going to change this now, and we're going to do a vertical stretch. So if you remember, I had that 3 on the outside here. There's a rule in multiplication. You can multiply in any order. It doesn't matter. So you'll notice it does the exact same thing if I put it in the front. We're just used to seeing it in the front, so I'm going to put it in the front. So we've taken a quadratic, and now we've multiplied it by 3. So what has happened...
So would that be A?
Yes, this is our A value, okay?
Yeah.
So our old A value, you can see here was one of the coordinates. It was at 1 and 1. You know what I should do? I should quickly... I can jump back and forth if I'm quick enough. Let's do this. That way I can write better. There we go. Whoops. Yeah. Okay. There we go. That's better. What's happened now is this is essentially taken the Y value and we've multiplied it by 3. So the X value stays the same. It's still 1. So at 1, I just go up 1, 2, and there it is. There's that new coordinate, 1, 3. And the same thing has happened over here. I'll zoom out a little, which is going to change. I won't zoom out yet, just because it's going to change. This doesn't like draw directly on the page. We go over, this is -1, but it goes up 1. Okay, and the reason it goes up 1 is because -1 squared, which is what a quadratic is, becomes +1. Great, so there's one of our coordinates, -1, 1. But to stretch it, we are going to multiply that Y value by 3, so we stay on the same X value. Instead of going up 1, we go 1, 2, and there it is, right on that point like we thought. -1 and 3. So this is a vertical stretch. A compression is a value between 0 and 1. So instead of using 3, you could use something like a half, and you'll notice it got much wider. We could calculate that one. And then finally, a negative will flip this on the x-axis. So if I hit this negative, there we go. The whole function has flipped downwards. Okay. And then the last one that's probably the trickiest, and let's go back. What we just dealt with there was our a value. To go back, I need to do this. Bring that down. There we go. So what we did is we just dealt with our a value. We did a stretch, we did a compression, and then we did a flip at the end with the negative. The last thing we're going to do is our k. So let's take a look at k here. K exists inside the function, and it's usually multiplied by the variable. So in this case, let's say it is 3. Okay. Notice that positive 3 looks like it's being vertically stretched, but what's actually happening? There we go. What's actually happening? So if I guess I should show it the other way too. What we did is we took this point originally when it was a vertical stretch, and we pulled it. Think of it like pulling an elastic band upwards. Okay, that's vertical. So we pulled the elastic band. It got a lot thinner on the insides. Okay. Oops. There we go. What we are going to do for horizontal, a positive value like this actually does a horizontal compression. It squishes it inwards by a factor of 3. So we're doing the opposite idea. A better number to look at would be 9. Let's zoom out just a little because that'll help us. There we go. I'm going to look at 9 here. The reason I'm going to look at 9 is I'm going to go to 3. Here's my 9. Whoops. Okay. This value here is 3 and 9. I'm just using it so we end up with nice round numbers. Yeah. When you do it here, what you're actually doing is you're dividing the x value by whatever's there. In this case, it's 3. So this 9 value, you'll notice we're still on 9 here, but instead of being at 3, it's currently, if I go all the way up, there it is. It's at 1, 9. So we've made a horizontal compression. So we've changed the x values here. So that's the difference between horizontal and vertical. They can look really similar, but you're manipulating a different coordinate. When we do vertical stuff, we're manipulating that y coordinate on the old point, and when we do horizontal stuff, we're manipulating that x coordinate. So then to look like a horizontal stretch, we actually make it a fraction. So I can say something like a half here, and it looks like a vertical compression. Think of an elastic band getting crushed downwards. But what's actually happened is we have a horizontal stretch. We pulled it farther. And it's technically by a factor of dividing by a half, which is the same as multiplying by 2. So for instance, this is one of our old coordinates. That's supposed to be a 1. We take the x value and we multiply by 2. And if we take a look at that, should be at same y value 1. What's the number here? Oh, sorry, the 1 is here. It's now at a value of, sorry, I'm looking at too high. We should be looking at the number 1. I had that coordinate wrong. Should be down here. That's 1 and 1, and when we multiply it across, we get 2 and 1 there. So I know that part was a bit confusing. But essentially, the reason I wanted to do it in this function notation here, I'm going to clear all this stuff. The reason I wanted to show you this way is because what we can do is we can write any function in there. So for instance, our original function for a root was like that. Let's say I want to vertically stretch it. I can say, instead of using q, I can change the name of it. I'm going to say r now. I'm dealing with that function, and if I want a vertical stretch, I'm going to make it a number greater than 1, and it looks like it's been pulled upwards. Okay. If I want a horizontal compression, which is going to look almost identical, I go like that. Not quite the same amount, but it did the same idea. If I want to shift it downwards, I go down 2. And if I want to shift it to the left, I'm going to say positive 4, and it's now shifted to the left 4 units. So by leaving it in this like function notation, I can change whatever function I'm referring to. A lot of times the way they'll teach it is they'll actually put it in like a quadratic form. So we'll call this, give it a new name. And we might say, for instance, -3 bracket. Actually, let's do root, since the root function is what we're doing. We'll go by 2 x minus 5 plus 7. There we go. So we got some crazy stuff going on. It has that curve feel to it. Because it was a negative, we flipped it. So now it's going downwards the other way. We gave it a vertical stretch, so it's going down much farther, being pulled vertically. We gave it a horizontal compression, so that's like doing it even more. We've moved it to the right 5 units. That makes sense from this point here. We've gone over to here. And we vertically moved it up 7 units. So there's there. And we could have done it one at a time. So if I had done it one at a time, we'll use the letter Y for this, just because I'm going to run out of letters. You could start with maybe our horizontal stretches and compressions are sometimes the easiest way to start. So if I say, hey, I want a horizontal compression of 2, there we go. We put it in there and we get this new red one. And then if I want that vertical stretch of 3, makes it go even more, but then we do the negative, it flips it. So we get that similar shape to the black one there. And then finally, hey, I want to shift it to the right 5 units. It's now moved it in line with this one, and I want to vertically move it up. And now it's covering the old one. So we did them one at a time, and that's usually the order. You do your horizontal stretches and compressions first, and then you do your transformations from there.